The structural similarity between alcohols and water lead to some similarities in physical properties between alcohols and waters. So before we look at this in detail, let's remind ourselves about intermolecular forces. In Chapter 10, we focused on three intermolecular forces. London dispersion force is one of those, and that is an induced dipole caused by the random motions of electrons. So for example, if electrons are in one particular part of a molecule, there'll be a partial negative. The other part of the molecule will have a partial positive, and then that partial positive will attract electrons from a nearby molecule, causing that molecule to have a partial negative and then partial positive on the other side. So they're very brief. And the more electrons a molecule has, the stronger that London dispersion force is. So an easy way to determine how many electrons something has without actually counting them is looking at the molar mass. So when molar masses are similar, we assume that there are similar number of electrons. So often when we compare physical properties like boiling point, we want to make sure that the molar masses of those compounds are the same to make sure that the London dispersion forces are about the same. So if we have nonpolar molecules, which hydrocarbons are, or hydrocarbon part of a molecule is, then London dispersion is the only force that those nonpolar molecules will engage in, and all molecules exhibit London dispersion because it depends on electrons, so all molecules have electrons. The next strongest force is dipole-dipole, and that occurs whenever a molecule is polar. So if we remember back from our Vesper days, geometry determines polarity. So we'll be looking for lone pairs of electrons. If something has lone pairs of electrons in its structure, then we will consider it to be polar. And if that molecule has electronegative atoms, then it's going to be even more polar. So we'll get, as we look through this chapter, we'll just have to remember that oxygen is very polar because oxygen is in phenols and alcohols and in ethers. And then hydrogen bonding is the strongest type of intermolecular force, and it also has the most select criteria. It only occurs between hydrogen that is covalently bonded, so I say here bonded directly, but covalently bonded to nitrogen, oxygen, or fluorine. So that's a very, very select criteria. And that hydrogen can, in that bond between nitrogen, oxygen, and fluorine, that hydrogen can hydrogen bond with a nitrogen, oxygen, or fluorine that is in a polar molecule. Now, boiling points are proportional to the strength of an IMF, so we often use those to kind of gauge the strength of an IMF because the liquid to gas phase transition, which is what boiling is, or part of it, the other part is the vapor pressure, is the same as atmospheric pressure. But the liquid to gas phase transition occurs when the molecules in the liquid phase have enough kinetic energy to overcome the IMF, or the intermolecular force. So the higher the boiling point, the higher the intermolecular force is. So if we look at alcohols, and I'm going to use ethyl alcohol here as our example. It's also known as ethanol. It occurs in our everyday life, especially in northern Iowa where we grow a lot of corn to make ethanol. These alcohol groups have this OH, so it meets the criteria of that hydrogen bonded to an oxygen. This hydrogen can now hydrogen bond. And when we compare the boiling point of ethanol to other compounds that have similar molecular weight, so this ether, dimethyl ether, or this alkane propane, we see that ethyl alcohol has a much, much higher boiling point. It's almost 80 degrees Celsius, whereas that of the dimethyl ether with a similar molar mass, so similar London dispersion forces, is negative 23 degrees Celsius. So it's a gas at room temperature. And propane has a boiling point of negative 42, so it's also a gas at room temperature. However, water, which has a similar, this OH part of it as well, has a high boiling point of 100 degrees Celsius. So let's take a look at that hydrogen bonding that occurs between water and ethanol. So these little dotted lines are used to indicate intermolecular force, and this hydrogen that's bonded to the oxygen can interact with the oxygen of a water molecule, which is going to have a partial negative charge. And so this hydrogen bonding is related to dipole-dipole, but it's much, much stronger than what we would calculate the dipole-dipole interaction should be. And so we see the same thing with ethanol. Now, ethanol has these nonpolar parts to it, these methyl groups. However, the hydrogen on that hydroxyl group can find its way to other oxygens in other hydroxyl groups on other ethanols, and hydrogen bond. And so ethanol hydrogen bonds like water, and thus has a much, much higher boiling point than compounds of similar molar mass.